As can be seen, all of the devices involved in Brayton cycle analysis are steady flow devices that can be analyzed by using steady flow energy equation SFEE. In our analysis later, we are going to neglect the term changes in potential and kinetic energy. Our steady flow energy equation will now become these expressions. Note that the term heat transfer and work will depend on the role or function of that respective devices. Now let's have a look on the method to analyze for each of the devices involved in Brayton cycle. For process 122 across the compressor, since this process runs isentropically, thus we can use the isentropic relations for the ideal gases. This relation can be used to find the specific temperature or pressure. Note that Rp is the pressure ratio P2 over P1 and K is equal to gamma, which is the specific heat ratio Cp over Cv. From the steady flow energy equation SFEE, since the compressor is consuming work and let's assume the process is adiabatic, we can get the expression of power input is equal to the mass flow rate times with the enthalpy at the outlet minus the enthalpy at the inlet, that give us in the unit of kilowatt or kilojoule per second. Since we know that for ideal gases, the enthalpy H is equal to Cp times temperature. Therefore, the SFEE is now becoming this expression. Specifically for our current example, we can have this equation. Process 223 heat exchanger heat addition at constant pressure. Pressure at state 2 is equal to pressure at state 3. From the steady flow energy equation SFEE, we know that heat exchanger only receive or release heat. For our case, it is heat addition process. Therefore, the term Q dot in is maintained. And there is no work involved in heat exchanger. Thus, our steady flow energy equation will now become this expression. And the enthalpy for ideal gas is equal to Cp times T. Thus, we have this equation. With respect to our example, the equation will be this expression. Note that the temperature at state 3 is the maximum temperature for this cycle. For process 324 turbine, similar to compressor, turbine also works isentropically. But before that, let's have a look at the pressure ratio Rp introduced previously. Pressure ratio Rp is equal to P2 over P1. We know that pressure at state 3 is equal to pressure at state 2, and pressure at state 1 is equal to the pressure at state 4. So, if we substitute P3 and P4 to the pressure ratio, it will become pressure ratio Rp is equal to P3 over P4. Thus, our isentropic relation for process 324 will now become this expression. However, this relation is applicable for simple Brayton cycle. From the steady flow energy equation SFEE, since the process is adiabatic and the turbine producing work W out, therefore the steady flow energy equation is now become this expression. For ideal gases, the enthalpy is equal to Cp times T. Thus, or in our case, the equation now can become this expression. For the last process, which is process 4:1 constant pressure heat rejection, pressure at state 4 is equal to pressure at state 1. From the steady flow energy equation SFEE, since heat exchanger is not a work-related steady flow devices and it was used to reject heat for this process, therefore the SFEE will become this expression. And if we substitute enthalpy with specific heat at constant pressure Cp times temperature T, since the working fluid is the ideal gases, the final steady flow energy equation will be this expression. With respect to our discussion, the SFEE will be this equation. We also can determine the backwork ratio RBW, which is the ratio between work consumed by the compressor over the work produced by the turbine. In order to determine the thermal efficiency, we are going to divide the power net output with the heat transfer input. Only for simple Brayton cycle, we can use this equation to determine the thermal efficiency. This will be the derivation for this equation for your perusal. The advantages of gas turbine is high power to weight ratio as used in aircraft power plant, quick start operation as in power generation, can be operated on liquid or gaseous fuel, and can be coupled with a vapor power cycle for greater thermal efficiency. And the disadvantages of gas turbine is low thermal efficiency, which led to high operational costs, high startup costs in power generation industry, and high maintenance costs.